Hello, and thank you for tuning into my talk entitled Orthogonal Methods Are Critical for Characterizing Nanoscale Colloids. My name is Jean-Luc Fraikin. I'm the CEO of Spectrodyne, and I'd like to start by thanking Mark Constantine for organizing this session and for inviting me to speak today. I'll talk a little bit about my company's technology, but my main point is to use a couple of very simple experiments to demonstrate to you the importance of using really just a variety of different measurement techniques to characterize the particle content of your sample. So I'll give an introduction of why particle size and concentration are so important, review a few different methods for measuring them. I'll spend a little bit of time describing microfluidic resistive pulse sensing. This is Spectrodyne's technology, MRPS, in case you're not familiar with it. Then show you two examples highlighting why it's so important to use orthogonal techniques. These are simple examples. Experiment one, we just measure a few different polydispersed samples and show an interesting result about light scattering based technologies. And then in experiment two, we apply essentially what we've learned in experiment one to see the impact of that in real world vesicle samples. So why first are particle size and concentration so important? Well, as you're undoubtedly familiar, nanoparticles are everywhere now in a huge range of products, right? They're in foods, they're in things like floor finish and paints and coatings, industrial materials like that. And importantly, especially during a pandemic, they're present in drug formulations. Moderna's new vaccine is going to be based on nanoparticle drug delivery. So in these cases, in all cases, the particle size and concentration are critical metrics because they inform us about the product stability. They can be indicators of instabilities, for example. It's important to have a stable formulation for product performance. And in the life science examples, these are critically related to safety and efficacy of the products, of the drugs. So how are people measuring these parameters? Obviously, the gold standard is electron microscopy. This very powerful technique. You get to see the particles in the sample. But of course, it's hugely expensive and it's not really practical for routine use. So this is the gold standard. It's a useful reference material, but it's not practical for routine use. Way more commonly is dynamic light scattering, DLS, or photon correlation spectroscopy, PECS. This is everywhere, essentially, in pharma labs. This is an optical technique, so it uses light scattering to measure the properties of the particles in the sample. But it's an ensemble averaging technique, so it has a lot of issues with polydispersed samples, and it's also not quantitative at all for concentration. Nanoparticle tracking analysis has been around for about a decade now. This is, again, a light scattering based technique. So it's using optics. But in this case, we're measuring particles one by one. And in the right samples, it can be used to measure the concentration of these samples. And we'll talk more about NTA a little bit later. Finally, I'd like to introduce Microfluidic Resistive Pulse Sensing, or MRPS. This is Spectrodyne's technology. It's an electrical technique, so there are no optics involved. And it measures particles by counting and sizing them one by one. And importantly, this is essentially a modern implementation of the Coulter principle. And the Coulter counter has been, gold standard for measuring large particles in cells, for decades. So what we've done is scale it down to the nanoscale regime. So let me give you a little bit more detail about MRPS. As I mentioned, it's an electrical detection technique. And it uses microfluidics, and that affords many different advantages, including a super small sample volume required. It's fast and easy to use, and our current range of particle size measurements is from 50 nanometers at the small end up to about 10 microns in diameter. Because it's an electrical technique, this is an important feature, is that it doesn't depend on the material of the particle, so it's agnostic to particle material, and so that means it's got applications in a huge range of material measurement cases. So we do a lot of work in life sciences, virus quantification, nanomedicine, drug delivery particles, etc. And we've also demonstrated, readily measurements of industrial materials ranging from floor finish, like I showed you before, to inks and things like that. So that's one feature because it doesn't depend on how well the particles scatter light. So let me describe why that is and how it works. So MRPS counts particles one by one and measures the concentration of them very directly. So the way it works is we'd take particles, we take the sample and we flow them through in a liquid through a bottleneck in the constriction. And every time it goes through, we get an electrical signal that looks like this. This is real data showing the measurement of one particle over time. You can see it's quite a short time scale. And every time a particle goes through, we measure essentially two things about the signal. One is how big the spike is. That tells us how big the particle is. And the other is how fast it went through the constriction. And that tells us about the volume of sample that we've measured. So we take counts and the volume measurement to directly calculate concentration. That was just a single particle. Now this plot is showing us a longer measurement over a minute or so. And every particle detected is highlighted here by red dots. So you can see this sample contains a range of particle sizes. And these particles are grouped in sort of 4 different bands of sizes. We can see that by looking at the histogram of counts directly. But since we know the volume of the sample that was measured, we can convert counts into concentration. And so this is an example. This is the final result for that measurement. We've got concentration on the y-axis as a function of size in particle diameter on the x-axis. And you can see this mixture was a mixture of polystyrene beads of 50, 90, 120, and 150 nanometers diameter. And so this is a very good resolution of the different components of the sample, and we can be quantitative over any size range in here. We've got a lot more information in my poster. There are links to videos to learn more about how this works and papers. So let's talk about measuring polydispersed samples and why orthogonal techniques are so important. So first thing we did was take a few different polystyrene samples. So this will be this experiment. And using MRPS, we can measure this sample accurately. It's a 208 nanometer particle. These are NIST traceable beads. And you can see that here we've normalized the concentration. And there's a nice clear peak right at 208 where we expect the particles to be. We can measure a different sample, 150 nanometer particles, and see the same thing, nice clear peak, and do the same thing at 94 nanometer particles. And so what we've done here is shown that the monodispersed samples can be measured accurately by MRPS. So what happens when we mix this together? Well, you'd expect some particles at 208, some at 150, and some at 100 nanometers. And that's exactly what we see with MRPS. So we get essentially the superposition of the 3 different particle size distributions in the measurement of the mixture. So this is a very polydispersed sample, and we're measuring the full distribution accurately. So what happens when we do the same experiment with a nanoparticle tracking analysis? For nanoparticle tracking analysis, NTA, the monodispersed samples are all measured correctly, right? So as expected, we get a peak at 208. When you measure just the 208s, you get a peak at 150 for just the 150s, and the same thing for 94. So this would suggest that the sensitivity limit of NTA, is at least 94 nanometers diameter, right? Because we've been able to measure particles that small accurately. In this case, what happens when you mix the samples together? This is the measurement you get. And obviously, the 94 nanometer particles are totally missing from this size distribution. They cannot be detected. And so what we learn from this is that we have to use extreme caution with NTA because the sensitivity limit depends on the sample, right? When you mix these together, you can't see the 94s anymore, whereas before you used to be able to when you measure them by themselves. So why does this happen? Well, it's really a fundamental limitation of the technology. And as you're probably well aware, it's based on light scattering. So, and the scattering intensity of light from particles scales super strongly with diameter. So it's actually it's a diameter to the power 6 dependence. So that means, for example, in this example, of the size range that we're measuring, 400 nanometer particles would scatter, more than 50,000 times brighter than 65 nanometer particles in the same, very close in range, but a huge difference in scattering intensity. And the way NTA works is that particles that are scattering very weakly and very brightly have to be imaged in the same video frame. And so there's essentially no camera that can handle this properly. And I would encourage you to go and try this experiment yourself. It's very easy. It's just a few different sizes of beads. You can even just do it too. This effect is common to all light scattering techniques, right? This is it's basically just that the big particles scatter way more light and they obscure the small ones in the measurement. It's very difficult to measure accurately in polydispersed sample. So let's move on and talk about real-world vesicles and the implications of this in those kinds of samples. So samples you might be dealing with. So in this case, we started with a reference vesicle sample, and we measured it by NTA. And this is a typical output from NTA for these kinds of samples. There's, very nice, clear, prominent peak. It tends to be in the 100 to 150 nanometer size range. And if you're a researcher looking at this, you would say, oh, great, I've got a population of vesicles around 130 nanometers diameter. That's great. We can measure the concentration. And we could even think about tracking the position of this mean or mode of the peak here. So if I go and tweak my formulation and see this shift, that many people use that as a meaningful indicator of what's happening to the sample and the formulation. Let's look at this sample in some other ways using orthogonal techniques. So first, I'm going to replot this data on a log scale. This is the exact same data as before, but now we've got a log Y scale, right? So the peak is still at 130 nanometers, but it's flattened out a little bit. Now let's use some orthogonal measurements to compare. So first with MRPS, here's what we see. So it's actually kind of a power law distribution that MRPS sees, which is a continuously increasing concentration of particles all the way up to the detection limit. In this case, it's around 50 nanometers for these measurements. So what's going on here? Well, so we need an adjudicator. So let's measure this sample by EM. And you can see here the counts for using TEM continue to increase monotonically all the way down to 50 nanometers and beyond. And so this is the gold standard, and we see that the MRPS measurements agree very well with the TEM measurements, and the NTA signal does not. So how can we understand this? Well, in the previous example that we talked about with the polystyrene beads, we saw that when there were bigger particles in the sample, which there are here, it's very difficult for NTA, it physically can't accurately quantify the small ones. And that's exactly what we're seeing here, is essentially a sensitivity roll-off from NTA as you get down to smaller sizes. And for this kind of sample, these are vesicles. This is the size range of interest. I mean, this is critical size range, and NTA is showing, 4 orders of magnitude off in concentration. So this is an example that highlights exactly why orthogonal measurements are critical, is that you can't see, you don't know what you're looking at unless you look at it in a few different ways. And that's the main point I'm trying to make here today. So particle size and concentration are important. They're important for all about the product, right? Product stability, its performance, and ultimately, in many cases, its safety and its efficacy. So these are critical metrics for assessing the quality of a product. And in order to do that properly and responsibly, ultimately, it's important to use orthogonal measurement techniques in order to get an accurate picture of what's in the sample. And ultimately, more knowledge about your materials will lead to better science, and that's what we all want, right? So thank you very much for your attention, for watching the video. If you have any questions, please feel free to email me. My email address is here. And please check out the details of my poster around this presentation. Thanks.